Hi, this is Paul from Foresight Tech. In this video, we are going to deal with the antiderivative, which is the inverse process of differentiation and the foundation for integral calculus. Let's see the outline. First, I will introduce the definition of antiderivatives. Next, I will summarize the basic formulas for antiderivatives. Last, we will practice 3 questions together about how to use the formulas to find antiderivatives. Let's see the material. Here is the definition of antiderivative. A function capital F is called the antiderivative of a lowercase f on an interval if, capital F take a derivative goes to the lowercase f for all the x and I, which means what? This is the definition. So let me highlight what does this mean. Okay, and if we know capital F, if we don't know lowercase f, what does that mean? Means to find a derivative, right? That's that process we call it the differentiation. And now we need to go backwards. We know the lowercase f, but we don't know the capital F. See, what does that mean? This means the antiderivative problem is just the inverse process of differentiation, right? Okay, so this is important because this is the foundation for integrals we're going to learn in chapter 5. Okay. Now we have a theorem. This is the most important theorem for antiderivatives. So if capital F, why always? Okay, keep in mind here for antiderivative usually we will use capital. We will use a capital letter to describe. Okay, the lowercase f we call it the original functions. Capital F like this, or capital G, or capital other letters we call it antiderivatives. Okay, so now if capital F is an antiderivative of a lowercase f, and then the most general antiderivative is capital F plus C. C is a constant number. Any constant number. What does this mean? This means if we find one antiderivative, see, F is one antiderivative. Usually we call the particular antiderivative. Let me write this down. Okay, which means if we know one particular antiderivative, and this is a particular antiderivative, which means we know one antiderivative and then you know all the antiderivatives, just plus C. Okay, for example, if we have another antiderivative G, and we know the difference between G and F, capital F, is just a constant number. That does make sense? If we know one particular function or antiderivative and then just plus any constant number, and that's all the antiderivatives. Okay, so this looks fancy, right? So amazing. But we are easily prove this is true. Let me go to see. If we know another, let me see another antiderivative. I use capital G, which means and the capital G take a derivative equals capital F take a derivative equals the original function lowercase f, right? And then we can look at the difference between G and the capital F is just a constant number. Okay, why? Because, can you see now what do we get? We will get the difference between capital G and capital F. Of course, is what? Is G take a derivative minus capital F take a derivative, which is F minus F. Say that's 0. Okay, now we have a function which is G minus F take a derivative equals 0. Do you remember? We have a result, right? Now what do we get? We get this function which is G minus F should be a constant function because take a derivative equals 0 at all the variable x. Okay, so this is already a proof for this theorem. Why? Because we know the difference between any antiderivative is just a constant number. Or you can do this. You can just plus f both sides. We get any other antiderivative is just equals f plus c. See, that's the results. Okay, so let me draw you a graph so we can have another understand. What's the relationship between this f and the g? Okay, if I draw this graph, if I draw f, capital F is just like this. If this is a capital F, particular antiderivative, right? One antiderivative, which means now what is g? You know, g is just f plus c. If c is positive, then it's shift up. Okay, so can you see? This is what? This is g, a particular. Okay, well, what does this mean? This means just shift the capital F up. Okay, if c greater than 0. If c less than 0, just shift the f down. Okay, which means these two functions just parallel to each other. Okay, so now what do we get? We get all the general antiderivative should be this cluster, a series of functions. All the functions just use the particular function f, shift up or shift down. Imagine. Okay, so infinite antiderivatives. Okay, so this is the basic introductions for the definition. Now, let's go into some formulas for antiderivatives. Here is the antiderivative formulas, and this is a summary. Not cover all the formulas, but most of the formulas we put here. Can we see? And the first column is the original function. The second column is the antiderivative. Okay, the one particular antiderivative. So if we need to find all the antiderivative, just plus constant number c, right? Okay, and look, there's a lot of formula, but don't worry. So all these formula are just trivial, because you know, if you know the derivative formula, and then the antiderivative is just the inverse process, right? Which means just look backwards. Okay, so this formula should be easy. Let's go into the first three. Okay, and then we just go through all these formulas together. So the first is what? If you remember the first formula, we call the what? The constant multiple, right? Constant multiple. Or if we put the first and the second together, what do we call? What did we call it before? So we call the linear property. Okay, so here is the same. We still call linear property. Okay, it's a linear property, and we are going to look at why the first is correct. Okay, can we see? So c is a constant number. So f, lowercase f, is a function. And if capital F is the antiderivative is a particular antiderivative of lowercase, and then c times capital F is the antiderivative of lowercase c, c times lowercase f. Why? Because this derivative goes to cf, right? So let me write this down. Because c times capital F, can you see? Capital F is a function. Take a derivative is what? We learned this, right? Linear property of differentiation. So there's c, capital C, lowercase c times capital F derivative. And therefore is c lowercase f. So is what? This is the proof for the first. The same, we can prove the second, okay, which is the sum law, right? We learned that before. If capital F plus g, see, take a derivative is capital F, take a derivative plus g, take a derivative is what? Is lowercase f plus lowercase g. So this is the proof for the second. Okay, we call the linear property. So we still keep. Now let's look at the third one, and this is a major one. Okay, very important. So let me go into see. Let me highlight this first. What does this mean? This means polynomial. This is what, not a polynomial. It's a power function, right? Let me put here. And you say this is just the power rule, okay? Do you remember power rule is one of the most important rule in differentiation, right? So here it just go backwards. See, x raised to the nth power, of course, n is not a -1. If it's -1, is the reciprocal. We have another formula, okay? So this power function has what? Has a steer power function as antiderivative, because what? Because power function take a derivative goes to power, right? So steer power. However, we have a coefficient. Can you see this? Okay, why this is true? Let's go to verify. Okay, I'll verify here on the bottom. So all we need is just go to verify x raised to n plus 1's power over n plus 1. If this is an antiderivative, which means this take derivative should be goes to the left. Is this true? Okay, it's going to like this. N plus 1 is the bottom. The top is power function take derivative. Everyone knows. Take down the power, and the new power goes to 1 less than 1, right? Which is -1. That's n. Now, what do we get? Okay, we cancel this common factor. Therefore, and the answer is x raised to the nth power. What does this mean? Means this formula is true, right? Okay, and we need to practice a little. Let me give you an example. How to use this power rule. Okay, so let me give you a simple example. So the first, if I give you x, what is the antiderivative of x? Okay, x, which means the power 1, right? If we use the formula, now x, so the power n equals 1. Okay, what do we do to find the antiderivative? Raise the power 1 more, which means 1 plus 1 should be 2, right? And the bottom denominator is divided by 2. So these are all we need, okay? And the basic way is just increase the power and divide it by the power, new power, okay? So it's this. And tell us is what is a new power, which is 1 plus 1 is 2. This makes sense, right? And then divided by the new power, so is 2. See, this is the antiderivative. Okay, so let me give you one more. If I give you x squared is the original function, can we find that the antiderivative, a particular antiderivative, is what? It's the power function, right? Okay, so the power rule give us is increase the power 1, which means the new power is the third, and then divided by the new power, which is divided by 3. Can you see? If I give you x4, so they are the same like that. Okay, moves on. Now let's go through all these other formulas. So 1 over x is reciprocal, right? Everyone know reciprocal. What is the derivative of this function? ln goes to absolute value of x. We have a formula before, okay? And the derivative of this is just a reciprocal. Therefore, ln x absolute value of x is one particular antiderivative of the reciprocal, right? Okay. So one more. Can we look at this function e raised to the x? We call the natural exponential, right? And that derivative is the self, because this take derivative equals the self. And then one more. If we look at the general exponential, b raised to the x, of course it's the exponential, right? However, we have a denominator is ln at b, because you can imagine then this take derivative, and we're going to cancel ln b. What we get should be b raised to the x power. So this is also true. And now let's move to trig function. Because sine take derivative goes to cosine, so the particular antiderivative of cosine is sine. That makes sense, right? And because cosine take derivative is negative sine, and therefore negative cosine take derivative is sine x. Therefore, negative cosine x is one particular antiderivative of sine. Okay, so this is another formula. And then let's move to secant square. You know tangent take derivative goes to secant square. Therefore, what? Tangent is the particular antiderivative of secant square. And the same we have what? We have a cosecant square like that, or it's a cotangent, negative cotangent. You can go or write the formula for yourself. Can we look at it one more? Is secant x times tangent x. Antiderivative is secant at x, because secant x take a derivative is this one, right? So this formula is true. Let's look at other formula. Here is a inverse trig function, right? Do you remember inverse sine take a derivative goes to 1 over square root of 1 minus x squared. Therefore, inverse x, inverse sine at x is the antiderivative of this, okay, big term. The same for inverse tangent, okay. And you know we have other inverse functions, right? Inverse trig, like inverse cosine, inverse secant, inverse cosecant, okay. Other formulas we did not write here. And then now we move to the last type of functions we learned before is what? Is a hyperbolic function. Do you remember hyperbolic sine function take a derivative is equal to hyperbolic cosine, right? Therefore, hyperbolic sine is the antiderivative of hyperbolic cosine. The same, because hyperbolic cosine take a derivative goes to hyperbolic sine. Therefore, hyperbolic cosine is a particular antiderivative for hyperbolic sine. Imagine we have other hyperbolic functions, right? And we also have other inverse hyperbolic function formulas, okay? So you can put everything together to make a big table for yourself. And these are all the formulas. See, look, it's nothing new. Just go backwards from the differentiation, okay? So we have all these formula. Now, let's go into practice this formula. Here is the first question, and we need to find the general antiderivative of this function. See, this is what? This is a rational function, right? We do not have a single formula, okay? However, and this is very easy to break down this rational function into small pieces. All you say is you're going to expand the fraction, or you say just simplify. Okay, so let me draw. We can do what? We can simplify this into a single power function. So we have the antiderivative formula to use. So the first is just simplify. Okay, break it down. This is a complicated fraction. So what do we get? We get this. I get f(x) should be equals x sixth power over x fourth power, right? Plus 3 times x fourth power over x fourth power. And then minus x the third power over x the fourth power. And plus 6 times x the second power over x the fourth power. Can you see? And this is an easy way to expand the fraction. Now we're going to simplify. See, what do we get? We have the first is x squared, right? The second term just go to 3. The third term is reciprocal. The last term is 6 times. Okay, I will going to write a power function, which means x raised to the negative 2th power. Okay, in this way, what do we have? See, and this power and this constant is their power. This is reciprocal. Okay, and this is the power. Each one we have a formula, right, from just the summary. Okay, so what do we have? Now we directly get. So now we can write down the antiderivative should be equal to this. The first, remember how to do a power function. Still has a power function as an antiderivative. However, the power goes increase 1, right? And then divided by the new power. See, easy to get this one. Now the second term, of course, easy. Okay, just 3x, because 3x take derivative is 3, right? And we have a formula for reciprocal, which is ln absolute value of x, right? Now the last term is 6 times. Okay, the power. Okay, x with the second power, negative second. The new power should be plus 1, increase 1, which is negative 1, right? And then divided by the new power, which is negative 1. Have you seen? And don't miss, what do we need? This is just a particular. We need a plus c. So that's what? That's the general antiderivative. Of course, we can simplify this term. Can you see this term? We can what? We can write in this. We can simplify just the minus 6 times x raised to the negative 1's power, right? So this is the first question. Now let's do another question. Here is the second question, and we see this question we call the initial value problem, because we have an initial condition. Let me highlight this first. Okay, we call the initial value problem because we have an initial condition. Okay, and this condition we can use to solve the constant number c. Therefore, okay, we can get a particular solution, not just the general solution. Okay, and one, can we see? The question asks to find the f, and they call the antiderivative. It's strange. Why f? We call the antiderivative because you know f exactly is an antiderivative of what? Of the derivative function. Does that make sense? Let me write this down. And can we see? Because what? Because f is definitely, okay, is an antiderivative of what? Of f prime. That doesn't make sense. Okay, because f take a derivative goes to f prime, therefore f is an antiderivative of f prime. So we know what, in this question we know the derivative, we don't know f. See, okay, so we still need to find the antiderivative. That's easy. Why? Because this power, this is power. Okay, so we just use the power rule. Is good enough. Let me, okay, so write a little. So first I will change a little for this f function. Okay, because f prime now I can write into power. The first is t 1's power. The second is negative 3's power, right? And therefore we use the power rule. What do we have? We have ft, which is the antiderivative, right, of f prime. Okay, so this time the first, you know, is what? It's the other power, but the power increase 1, which is 2, divided by the new power. Okay, and then plus the second is power, so we increase the power 1, which is negative 2, divided by negative 2, divided by the new power, and then plus what? Plus c. Don't forget it. Okay, and let me write a little bit another version, which is this minus, right? And the t raised to the negative 2's power over 2, and the plus c. What do we get? We get a general antiderivatives. This is the general antiderivatives, covers all the antiderivatives. What do we do now? Okay, don't stop at here, because we have an initial condition, which is f1 equals 6. We can use that equation to solve that information to solve for c. Okay, so we can get a particular specific antiderivative. Okay, so I was going to use that information, which is what? Which is f1 equals 6 was f1. F1 is a log t equals 1 into that formula, which is 1 over 2 minus 1 over 2 plus c, right? The condition give us this 6. See, what do we get for c? Of course, c equals 6, right? That's good. Now what do we conclude? So we have a specific solution or antiderivative, which means f of t equals t squared over 2 minus t raised to the negative 2's power over 2 plus c. C this time is 6. Can you see? This is a one function, exact function. We resolve this initial value problem. Okay, now let's practice one more question. Here is the last question. See, is still initial value problem, right? And we need to find the position of the particle given the acceleration function and the initial condition. So how to find this? Do you remember in differentiation rule we have this? If we know that the position function, we can find the acceleration. How? Okay, take a derivative of the position function s, we get the velocity function v. Do you remember that? And then take the derivative of the velocity function v, we get the acceleration, right? 2 steps. Therefore, these questions we need to go backwards. Okay, so there are 2 steps. Okay, antiderivative of acceleration will be the velocity function, and then the antiderivative of the velocity function will be the position function, right? So this is a famous problem. Now let's going to do these 2 steps. So let me highlight the definition. Okay, so here we need to find the position. Let me give the position, we use s, because in the question they already use position function, we use s. Okay, and another is the velocity, we use v. This is the setup. Okay, so the first step we have to use this. We have to use a v, take a derivative. Remember, is a, right? The derivative of the velocity is acceleration. Therefore, what? Therefore, velocity is antiderivative of acceleration function, right? Okay, so now it's not difficult. So we can going to find what? We can find a vt should be equals antiderivative of at, easy to find. So is t raised to the 3rd power over 3, right? Minus 4 times t increase 1 power, okay, over the new power 2. 6, we have the antiderivative is 6 times t. Don't miss plus c. Because we have 2 steps, and therefore we will have 2 constant number. So it's better I give you c1, okay, and they simplify a little. So what do we have? This is t the 3rd power over 3 minus 2 times t squared plus 6t plus c1. So now good, we already find the v. What do we do now? Okay, so we need to move on to find what is s. What's the relationship between s, the position, and the velocity? See, we have to use another relationship, which means s take a derivative equals v. That's famous, right? Okay, therefore s is the antiderivative, particular antiderivative of v. So we get the general solution first. Let me see. Now what do? We can find what is s, antiderivative of v. We know v. Therefore, step by step, we're going to write. So 1/3 is a constant. Let me write 1/3 here times what? Times t raised to the power of 4. Antiderivative is going to increase the power by 1. Okay, over the new power. And then minus 2 times increase the power 1, so 3 over the new power 3 plus 6 times increase the power, so goes 2 over the new power. Can you see? And the c1 is a constant, so we have a c1 constant number times t, right? This is the antiderivative. Don't miss, we have to plus c2, right? The second constant number. Okay, so we're going to simplify. Now, the first we have t raised to the fourth power, right, over 12 minus 2/3 times t raised to the third power plus 3 times t squared plus c1 times t plus c2. So good. Now what do we do? So this we call a general solution, right? General antiderivative. And see, we have an initial condition. We have to use one information, two information. We can use that two information to what? To solve this constant number and this constant number. This is the second step. Now, that's going to solve this C1 and the C2 by the initial condition. The first is S at 0 equals 0. Okay, so we're going to do the first, which is this. Remember, the initial is S at 0 equals 0. Okay, did the first. I will use this to find the equation. How to do? Plug 0 into the function s at 0, right? Which is 0 minus 0 plus 0 or the 0. So c1 times 0 is still 0. So c2 equals 0. Okay, so easy to find. C2 we get the 0. What the second? Let's go back to check. See, s at 1 equals 20. The second condition is x at 1 equals 20. So that's s at 1 equals 20. See what we can get this time. 1 plug in, which is 1 over 12, right? S at 1 is this minus 2 over 3 plus 3. C1 is 0, we don't have, and then plus C2, yes, plus plus C1, right? C2 equals 0, C1 we don't know. Okay, so C1, and then we get 20. See, that's a linear equation, simple. Okay, and then we do calculation. See, I get C1 equals 211 over 12. It's already. So now what do? We can conclude a specific solution is this one. Okay, we can conclude. So the specific solution, which is s at t, specific position function is this: t raised to the fourth power over 12 minus 2/3 times t raised to the third power plus 3 times t squared. C1 is what? Is this fraction. So plus 211 over 12 times t, right? C2 is 0, so that's all. Can you see? This is the particular solution, antiderivatives. That's all. Thank you. I hope you enjoy learning on this topic. If you have any question, please leave your comment. If you like this video, please give me a thumbs up. Thank you for your support. Please don't forget you are very welcome to subscribe to my channel for more videos. In the next video, let's see, we will move to chapter 5, integrals. Hope to see you there. Thank you. Have a nice day. Bye.